In this recording, we'll work a few capacitance examples. Okay, this first question is a simple question. How much charge is on a 0.9 farad capacitor which has a potential difference of 200 volts? Okay, now, of course, this means how much charge in each plate. One plate is going to have a charge of plus Q, and the other plate is going to be a negative charge minus Q. Now, the overall net charge in a capacitor, remember, is 0. But Q is just C times V. In this case, that's going to be 0.9 farad, which is a huge capacitance, times 200 volts. So that gives us 180 coulombs. The unit for charge is coulombs. Farads times volt is coulombs. Unit of capacitance, farad. Unit of voltage, volts. Farads times volts is coulombs. How much energy is stored in the capacitor is 1/2 of CV. 1/2 of CV, that's going to be, no, what did I say? 1/2 of QV. Okay, just to, my memory did fail me there. Okay, that's the equation. It's 1/2 of Q times V. One half of QV, so in this case our Q is 180 coulombs. Our V is 200 volts. So it's 180 times 100. So that gives us 18,000 joules, or 18 kilojoules. Okay, let's check this other example. Calculate the capacitance of a parallel plate capacitor made from two large square metal sheets 1.3 meters on a side, separated by 0.1 meters. So this distance is 0.1 meters, and they are square metal sheets where this side is equal to this side, and they are equal 1.3 meters. Okay, so that gives me the area. Area should be 1.3 meter square. Okay, I'll calculate that on the side. Which is 1.69 meters squared. Now, the capacitance is epsilon 0 A over D. So that's going to be epsilon 0 is given to us here. It's 8.85 10 to the minus 12 coulomb squared over Newton meter squared, times A, which is 1.69 meters squared, over D, which is 0.1 meter. I'm calculating it on the side here. So I get something like 1.5. Then we have times 10 to the minus 10 excuse me, farads. Okay, now just I need to verify my 10 to the minus 10 because my calculator didn't do that for me. I had to count the zeros. So we have 8 times 1.69, that gives me something in about 10. 10 divided by 0.1 gives me something about 100 times 10 to the minus 12. That gives me something 10 to the minus 10. So that's correct. Okay. Let's work this question here. What happens when you double the charge on a capacitor? So we have a capacitor and we manage to put on it twice the charge. Okay. Initially, the voltage across the plates of the capacitor is given as E0 times D. Call it the electrical field here E sub 0, and then we'll find whatever it is here. Now, what do we know? We know that the capacitance is related to the charge through this expression. Q is equal to CV. Now, if I double the charge, the capacitance does not change, since I'm not changing what's in between the plates, the separation of the plates, or the size of the plates. I'm not changing any of these, so the capacitance does not change. Now, if the capacitance does not change and I double the charge, that means the voltage doubles. So VA minus VB is actually twice the voltage that we had here, or twice E0 times D. That means, since V should be equal to E times D, that means the new electrical field is just twice E0. So what I do, I actually double the electrical field between the plates if I double the charge. Now in this question here, we have a parallel plate capacitor. This side is charged positive, this charge is charged negative, and we pull them apart. What happens to the charge Q on each plate of the capacitor as we pull them apart? Okay, since it does not say that we are going to connect them to anything else, if there is no leakage, there is no reason for the charge to go anywhere, so it should remain constant. It does not matter what happens to the capacitance, the charge had nowhere to go. If the charge had nowhere to go, we should have conservation of charge, and the charge has to remain constant.